Yo, what's up, guys? Welcome back. Episode 138 today, I think. Um, yeah, 137. Yeah, we did that one yesterday, so 138 today. We have an Omninite and an extinct Pokemon, from what I remember. Um, yeah, appreciate all the comments and everything on the last video. Again, it keeps me going, and it's fun making these videos. So yeah. Let's just jump straight into it. Let's check out the Omninite Pokemon sound. Let's take a look.
Still looking for a new job?
Just found out my dad's sister's husband is golfing buddies with the CEO of a great company.
Yeah, man, all these sounds are so difficult to do. Dun-dun-dun. I don't even know. Dun-dun-dun. 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 I don't know how to. So hard to do the sound, but yeah, that's our sound today. We're gonna jump straight into Leetcode. So let's see what our problem of the day is today. Kind of plan on hopefully doing a few problems. Maximum difference between even and odd frequency to 25% acceptance rate. Man, there's been a few hard problems of 4 days in a row, but I think I'm gonna leave this for now. We're gonna finish off our Leetcode 75. I know we struggled with this one. Then we got domino, trombino, tiling. I think what the goal is today is we'll check out these two problems and maybe do a graph problem depending on time. So we'll take a look at these. Take a look at this one. Given three positive integers A, B, and C, return the minimum flips required in some bits of A and B to make A or B equals C bitwise OR operation. Flip operation consists of change any single bit 1 to 0 or change the bit 0 to 1 in their binary representation. Okay, so we've got A is equal to 2 here. Okay, in binary, we got B is equal to 6. This would be 1, 2, 4. Yeah, so this is 6. Our C is equal to 5. Okay. After flips, A is equal to 1, B is equal to 4. C is equal to 5, such that A or B is equal to C. The intuition isn't coming to me right now. Check the bits one by one whether they need to be flipped. Well, obviously I knew that, but the only thing that comes to mind for me is doing some sort of like maybe some recursive algorithm that can check all possible combinations that just keeps flipping everything. Either you flip or you don't flip, you flip or you don't flip, and eventually we'll find something that with the AND or B. But obviously that's hella expensive and that a little bit too long. Yeah, the time complexity here is crazy big. Is it just a bit manipulation problem? I am not sure, to be honest. I really don't know how to do this. So I guess what they're doing here is they're flipping here, right? So they flip. So this is 2. So this is 2 flips here, right? Because they flip 1 to 0, 0 to 1. And then they flip what do they do here? They flip just this one here, right? Makes it B, and C is equal to 5. After flips A1, B is equal to 4, C is equal to such that A or B is equal to C. Now A or B, all would be, man, I'd have to like probably look at the truth table, right? But looking at this, I think if they're a 1, they're going to be a 1. Let's take a look at the discussion. You would think this should be an easy. Wow, but says the guy who solved 800 plus probably disagrees. I'm just saying. Yeah, I'm. Another genuine 5-minute problem. Thanks for that, man. It gives me some hope. The thing is, I have to figure out, okay, like, what is the trick, right? Obviously, we got to use a for loop and loop through, but what is the trick that... Maybe we should watch a video. Because I'm not good at bit manipulation problems. I don't really understand them. I don't want AI mode. Take a look at some videos. Does Leetcode have a video? Damn, man. Leetcode doesn't have a video on this one. That's frustrating, dude. I'm gonna take a look at this 5-minute video just because it's quick.
Hey everyone, welcome back. Today we are going to solve problem number 1318, minimum flips to make A or B equal to C. First we will see the explanation of the problem statement, then the logic and the code. Now let's dive into the solution. So in this problem we are given 3 inputs, A, B and C, and we need to perform bitwise OR between A and B, and when I perform bitwise OR between A and B, that value should be equal to C. So I need to calculate the total number of flips that will make this equation valid. So I will show you guys with the example, then you guys will be able to understand this one. So here we have the binary representation of A, B and C, that is 265. Then I will initialize a flips variable which will be 0 at the start. So here I have the template of the particular equation. So here we will pick the values from A and B, and this will be C, right? And this plus operation denotes the OR. So now I will pick the rightmost value from the binary representation, right? So 2, 6 are A and B, and 5 is C, right? So we pick the rightmost value of A and B first, that is 0 and 0. Then C is 1. So what are the ways that I can flip A and B to make this equation valid? So in this case 0 plus 0 is not 1, right? So I can flip both A and B to make this equation valid. That is 1 plus 1 is 1 in bitwise OR. And there is also another case where I can flip either A or B, 0 plus 1 or 1 plus 0. Both will give me 1 as well. So the minimum flips I need to calculate here. So here I can flip 2 times. Here I flipped 1 time, and here 1 time as well. So the minimum flip I can make this equation valid is 1. So I will increase the flips by 1. So we should not flip C. We should only flip A or B to make that particular value equal to C, right? So now I will discard all the rightmost values since I have done with those values. Then I pick the next set of values, that is 1 and 1. So from A and B we are picking 1 and 1, and C is 0. So now again this equation is not valid. 1 plus 1 is 1. Actually it is not 0, right? So how many times I can flip A and B, I need to check now. So in this scenario, I need to flip both my A and B to make the equation valid, right? So we are flipping 2 times.
Oh yeah.
So here if I flip only 1 time, either A or B, I will be getting 1, which is not a valid equation here. So I'm in a situation where I need to flip 2 times. So I will flip both A and B. So the minimum flips I can make in this iteration is 2. So I will add 2 to the flips. So now the flips becomes 3. So I will discard all the values right now. Then I will pick the next set of values from the binary representation. Since A is null, we will be taking 0 here. So we pick A, B. So here A is 0, B is 1, and C is 1. So here in this case, this is already a valid equation. 0 plus 1 is 1. So we don't have to increase our flip here. Then I'm done with all the values. So I can just return flips. Then I can just return the variable flips, that is 3 in this case. This is the minimum number of flips I need to make the equation valid, right? That's how the logic is. Now we will see the code. Before we code, if you guys haven't subscribed to my channel, please like and subscribe. This will motivate me to upload more videos in future.
Okay, I think I understand. So what we're gonna do is we're gonna create a for loop, right? So well, actually, 1, 2, 3. So number 1 is equal to bin A. 2 is equal to bin B. Bin C. I'm gonna see. I'm curious to see. Does this work, dude? I don't know. Oh, jeez. Let's check with GPT. See how this works. How do I? Okay, these are integers. Okay, yeah, we need to slice off the first 2 integers, so do we need a return or something? Typo. Return A. Is it the return that's messing with it? Okay, yeah, it is. Okay. std out 1 0. Okay, let's print our print 2, print 3. Is this going to be an issue though, being at the rightmost value? I think so. Right, because right, if we always start at the rightmost value. Unless maybe not, I don't know. Just do like flips equal to 0. Print 1, 2, and 3. We do a for loop for I in range length. Let's maybe, do we hard code to the biggest number? Maybe we can do it like that, where we can hard code to the biggest number. So we can do, well, like, this probably isn't the best way to do it, but I think this will work. Big number is equal to the max of A, B, C. Print big num. The biggest number is 6, right? So then we do big num is equal to the bin of big num Does this work then? The length of big num is 5. Oh, that's right, because we're not taking off the first two numbers. 3. Okay. Alright. So we get the length of big num, right? Come down here, do the rest of these, right? Then we do a for loop, right? We do, well, for I in range big num. Okay. I think will that loop backwards, I think. Will this for loop backwards? Yeah, okay. Yeah, we want to do n minus 1. Yeah, big num minus 1. That's what I was thinking. Alright, big num minus 1. Okay. Then we would go, okay, well, so these are integers. Are they strings now? I don't know. Let's take a look. 1. Let's print 1 I. See if it's a string. I think it said in GPT that this is converted to a string. String index is out of range. Oh shit. This for loop isn't gonna work, man. Because the first iteration is out of range, right? We don't have a 3 or a 2. Oh, okay. Apparently there's this function called zfill. String method in Python that pads a string with zeros on the left side. It takes an integer amount width, which specifies desired length that results in the string. Okay. Zfill big num. I was literally about to search it up on the internet, and GPT already told me that I'm gonna need this, so I was like, okay, let's stick with that. Zero, 1, 0. Okay, perfect. Okay. And it prints, yeah, 0, 1, 0, which would be the first number here. Okay. So now we do, okay, well, we loop backwards and we do, okay, well, if 1 I or, is that how you do it? Or, wait, okay. So we use the pipe. Okay, so if 1i or 2i is equal to 3i, well, if it doesn't do that, if it doesn't equal this, right, then check if both 0, right? Because if they're both 0, right, let's do or truth table, right? If we look at our truth table here, we see or if we have 2 zeros, then we know we're going to need 2 flips. Otherwise, we know we're going to need 1, right? So if 1i is equal to 0 and 2i is equal to 0, then we do flips plus or equal to 2. Otherwise, we know that it's 1. And then we return our flips. I don't know if this is going to work, but maybe we're going to have to cast this into an integer. Cast this all into an integer, dude. Here we go. Oh, we're getting somewhere. Well, here we're gonna need. We got 2 zeros, so we're gonna need. Right, we do 2, 1, 1. Oh, but if they're both 1. Not 2 return flips, dude. Did that make a difference? I don't even know. So we're missing something here. I don't know. I don't know what it is. What are we missing here? I thought it was the 1, 1, but I don't know. Oh, so they're saying instead of casting it, wait, hang on, you're very close. This issues the condition. Here, 1i and 2i as strings. So you should compare them 0, 0, not 0 and integer. Also, your logic needs to consider the actual rules of the problem. If c-bit is equal to 1. So I think that's what we're missing here, right? So if a bit is equal to 0 and b bit is equal to 0, we flip once. Otherwise, c bit is 0, we do, well, so we have this does not equal this. Then we do, well, we can do, well, if int c is equal to 1, then we need to do, well, if, so it'd be int 3. If int 1 is equal to 0 and int 2 is equal to 0, right? Then we need to flip once, okay? Otherwise, if we would do, well, if it's 0, then else, if int 1 is equal to 1, flips plus or equal to 1. If int 2 is equal to 1, flips plus or equal to 1. Right, so if it's 0, then we would return. Nope. Okay. Let's look at this truth table. If we have a 0, right? Okay. If we have a 0, then for it to be 0, we need 2 zeros. Okay. Oh shit. 1i 3i. God, I totally forgot to put I. Well, that makes a difference. Flips. Oh man, stuff pisses me off, dude. Network error. Nice, dude. Let's go. Okay. So if int I is equal to 1, then we check, well, if int I is equal to 0 and int I is equal to 0, we only need to flip once, right? Because if they're both, we need to flip 1 to get to 1. Okay, otherwise we don't need to flip at all, right? So that makes sense. Okay. Else if it's 0, then if int 1 is equal to 1, we need to flip 1. And if int 2 is equal to 1, we need to flip 1 as well. So that makes sense. Okay. Let's submit that. We might have to remove all the print statements for it to pass, but no, it passes. Okay. Like it's so low. Curious what the time complexity of this is. I think it's just like O of n, but log n. Okay. Nice. That was a good problem. Let's push that. Okay. Nice. Let's jump into a graph problem. Do one graph problem. Let's take a look. Study plan. Take some graph theory. Minimum genetic mutation. Let's take a look at this. Why is this a graph problem? I don't know. A gene can be represented by an A character long string with choices A, C, G, and T. Suppose we need to investigate a mutation from a gene start gene to a gene string N gene, where one mutation is defined as one single character changed in the entire gene. AACC. Okay, it's one mutation. And the game bank. Return the minimum number of mutations needed to mutate start gene to end gene. Okay, I'm a little confused here. AAC GGTTA. I'm really understanding this problem here. Leetcode is paying off. Good on you, bro. Good on you. So obviously it is a BFS problem, but I'm curious to know how you would run BFS on this. Would you run BFS on this? And you would do, okay, well, so we start with this, we add this to our queue, we check A, right? Well, if A 0, right, we can pass in the index number 2 is equal to this, we leave that, right? Then we get to a value that's not, right? So we get to A, get to here, right? We check, well, okay, well, is there one of these inside of here? Yes, there is here, right? Sorry, here, there's an A. Oh wait, no, N gene is double C. Okay, never mind. This is the same. AACC. Oh my god, I'm looking at the wrong one. I'm looking at the wrong one. So we see AA here, and we see AAA over here, right? So if this C does not equal this A, then we look inside of here, and we try and find one that does. As you can see, we have one right here, right? So then we can match it. Okay. GGTA. That's what I'm thinking. Is that right? I don't know. From collections, import DQ. Right, so what can we do here? Well, let's create our queue. Right. Let's append. Okay, let's do for I in start gene. For I. For val index in start gene and enumerate start gene. Let's append q.append. We append our val and we append our index, right? Append for q. Okay. We do while q. Okay, we would append our pop our index, sorry, our val u, and our I is equal to Q.pop left. Okay. We pop it. We check, well, okay. Are they different? Right? So if start gene I does not equal end gene I, okay, we do something about it, right? Well, like, okay, well, now I realize this is not gonna work though. Note that the starting point is assumed to be valid. I don't really get what this means, to be honest. If start gene does not equal end gene, then we check, well, okay. For I in range for C in bank, if gene I is equal to equal to end gene I, then we can return, I guess we can have a mutation here is equal to 0. We can do mutation plus or equal to 1. Else if we get here and we can't find anything, then else I think we can return -1. Because it's impossible to find anything, right? Because we can't find a mutation. Okay, wait, we wouldn't return -1 here. Because if we find something, it's instantly going to return, right? So we would probably return outside of this. No. How would we return -1? We got gene I mutation. Maybe we can make some sort of like flag or something. Right, so every time it comes here, let's create like a flag. Let's do flag is equal to false, right? If it comes in here and it sees this, okay, the mutation plus equal to 1, we can do flag is equal to flag is equal else. Flag is equal to false. We can do flag is equal to true, right? If we come outside of this, right, If flag is equal, right? Check if found, right? If flag is equal to false. False, we will return -1. Something's gonna go wrong here. I know this is gonna go wrong. Alright, if we find our thing, we can just continue, right? We continue. And then we're gonna return the minimum number of mutations. There's definitely something wrong here, bro. There's no way this is right. Like, why? Wait, string indices must be integers, not string. Can I just cast it like this? Can we do like int I? Sorry. I is equal to int I. Is that a better way to do it? Valid literal. Okay, I'm not sure, dude. I'm not sure why I'm getting this issue here. That's what I'm kind of doing BFS on. I did like incorrect use of enumerate start gene. Enumerate returns index char, not char index. Oh. Probably thinking about it wrong. In each step, try changing one character each position to one of the following allied nucleotides, A, C, G, T, and not yet visited, and queue it. Keep track of the mutations. Okay, I completely messed it up. It was a decent attempt. Maybe. If you want to call it that. It did say I was close. Oh, it says I was on the right track. Guess that's a little different. Right? I'm sure this makes sense, right? If Engine is not in our bank, we can return -1, right? Because if Engine is not in the bank, we can simply just return -1. That makes sense because our bank is just given like this, right? I'm going to do our genes is equal to A, C, G, and T. Okay. Bank set is equal to set bank. I think we use a set here of 1 lookups. I think that's why we're converting it here to a set. Bank set is equal to set bank. Then we create a visited set. Visited is equal to set. We create our queue. Q is equal to DQ. And we're going to Q dot append. What are we doing here? We're doing start gene 0. So we're appending the whole string. That's interesting. I don't know why we'd be appending the whole string. We would go while Q, we get our gene, and we get our mutation count is equal to Q dot pop left. Okay. If gene is equal to endgame, we return mutation count. Okay, if gene is equal to end gene, we return our mutation count. That's how we exit our BFS, right? We return the mutation count. Otherwise, we loop for I in range length gene. Okay, so we loop through each number in our gene. And we do, okay, so for G in genes, which is our one up here, if gene I does not equal G, why are we checking that? Is not equal G, then mutated is equal to gene I plus G plus gene I plus 1. If mutated in bank set and mutated not in visited, I don't get what it's doing here. They kind of lost me at this part. If mutated is equal to gene I plus G plus gene I plus 1. Okay, let's just go along with it, right? Mutated is equal to gene, and we slice from up to I plus G so we're actually making the change, right? And then we're doing plus gene I plus 1. Gene I plus 1. Then we check, well, if mutated in bank set and mutated not in visited. Okay, we do visited.add mutated q.append mutated mutation count plus 1. Outside of this while, we return -1. Okay, let's go through this again. So I think this is actually creating the gene, right? This is actually creating the gene that we're going to check inside our set, right? Which is technically our bank here, right? We create this, we make the change, so we see that something does not equal, right? If gene I does not equal G, let's just... Okay, so for I in range length gene, for G in genes, right? So we check genes and genes. If gene I, so the I that we're currently looking at, does not equal G, so we're changing gene, so gene, the rest of I, plus G, plus the gene before it. If mutated... Okay, I'm not sure. I thought I was getting it, but I'm not. Can you explain This part. This is the only part I'm confused about. You're iterating of each position of the current gene, and you're looking for where you could try mutation. For each position, you try replacing the current character with each possible gene character A, C, G, T. If gene I does not equal G, skip the replacement if the character is already G. No point mutating to the same letter. Mutated is equal. This conducts a new gene string by replacing character at position I with G. That's what I knew. It's a brute force approach, but instead we use white. So the way I was thinking about it before was the brute force way, right? You know, where we compared each letter to every single possible thing, and there could be thousands in there, right? Like what GPT was saying, but instead this is the better way to do it because we're comparing each of the different genes to each number in here, and if there's only 4 that we compare with, then really we're only trying, you know, a set amount. I think it said like 24, because 3 times 8 is 24 possible mutations per gene, right? Which is technically faster in terms of bigger problems. So that's why we're doing that here. Does not equal G. We're making them mutated. This is literally just making mutated. We change the character G here, right? Then we check, well, if mutated in bank set and mutated not in visited. So if mutated in bank set. Okay, why do we check if it's in bank set? Why do we check? Change a gene at a specific character. It's good, but we with that check. I hope GPT can understand my nonsense. One character mutation list. AACC GGT AAAC GGTA. Right, so pretty much what I think this is saying is that all the genes are in the bank, right? So you don't need to, the reason why we check if it's in mutate is because it's guaranteed that if we change one, that doesn't really make sense. If we change where that's like it, then it'd be there. I understand the fundamental behind this and the way that this algorithm works. It is definitely an interesting problem, but okay, I'm going to leave it at that. I think I understand. I'm a little confused, but I think we're going to revisit this problem again in the future. So, which, yeah, we probably should have done the brute force approach, but I don't know. It's okay. We'll leave it. We had the idea behind it. We had the right idea. We just couldn't really execute in the end, but that's okay. That's all about learning. So, appreciate you guys watching, and I will see you guys tomorrow.